So hello again. This is Roger Koch-Barr for the Bioelectricity course. We're in week 5, and this is lecture segment 10. In this segment, in this whole week, we've been talking about laying the track. And now I'm going to do something unusual and attack the work that we've just done and tell you why it really does not make sense. Let's look at it in more detail. So in our preceding sections, those sections pretended to show, I will say, that membrane currents can be determined directly from Vm values without computing the ionic currents. Now, we said in an earlier slide something like Im is equal to Vm1 minus 2Vm2 plus Vm3, and this was divided by some stuff down there in the denominator that involved the resistance, and we claimed that you could actually find a value of membrane current in that fashion. So now let me tell you why one should be skeptical of this claim. And as a matter of history, I can tell you I have worked with many people, especially students, who did not feel that this was the right way to do it. And they were smart, thoughtful people. And what they said was the following. They said, look here, the way that we do this is based on the fundamental definition that we've used over and over. If we want to find the membrane current, we define membrane current as the capacitive current plus the ionic current. So therefore, what we should do is we should get the ionic current according to the Hodgkin-Huxley model or some other membrane model. We should add it to the capacitive current, and then we will have the membrane current. It's as obvious as 1, 2, 3. And at the same time, it's equally obvious that you must find the membrane current by first finding the ionic current, because only by first finding the ionic current can you do this addition. Well, that seems pretty sound argument when you listen to it that way. And if you accept the argument as being true, you would say, whatever all this stuff is over here on the left, is that really right? I mean, really, think about it. But now let's look at it the other way around, more from the point of view of this week, rather than the week that talked about Hodgkin and Huxley. If we accept the definition that we have, that means we also accept the equation that turns these around. The capacitive current is the membrane current minus the ionic current. There's a little bit of culture shock here because each of us has become accustomed, in recent years especially, of reading equations not as mathematical equations, but as equations written into a computer program. So if you accept the top equation as an equation written into a computer program, you accept this equation as a directive as to how to do a computation. And the directive is, first you start with the quantities on the right, and then you compute the quantity on the left. However, if you just accept the equation as an equation in the mathematical sense, then of course if you'd accepted the top one, you've accepted this one too. And the bottom one turns out to be the one that we would rather use. So let's work with it in a mathematical sense. If you do that, then you can do the following thing. You can get the ionic current from the state variables, just as the argument has been made that one should do. You can get the membrane current from the neighboring cells as well as the home cell. And you can put that here as a second term. And then the consequence is that you can compute, you can actually find the value for the capacitive current, which it turns out is the hardest one to find, because there's no other way to get the capacitive current except through use of the equation on the left in one of its forms. So, while we started out skeptical, we see that what has been described in this week's work with the track is not only correct, it's correct and essential, because we have to use it as a way to find the capacitive current and thereby to find dVm dt or any of the other things that we want to compute from time to time. Let's look at this more informally in yet another way. If we start with the equation IC equals Im minus ion, it is as if the following train analogy was true. Suppose some robbers stop the train. They stop the train and they demand a ransom of $100,000. In that case, the membrane finds that Im is forced upon it by its neighbors. Or in this case, the train finds that these robbers have stopped the train and demanded a payment of $100,000 to let it go forward. Now, of the total Im, some of the current flows as ionic current. So we've got to have the membrane current because that is what is demanded by our neighbors. We can compensate and provide that to some degree by the ionic current. Therefore, we subtract it from the total that's required. But if the train company and the train engineers cannot come up with the whole payment of $100,000, they just don't have that much in the mail car, say, which is what's always robbed in the movies, then the robbers will demand the remainder from the rest of the train, from the passengers on the train, and they'll have to get out their purses and empty their pockets and come up with the rest of it. And in a certain analogous way, that's what happens in the equation. If the total of the membrane current, total this total, if that membrane current total cannot be fulfilled by the ionic current, the money in the postal car, then the difference has to be made up by the passengers on the train, from the money in their pockets and in their purses. So the capacitive current is that residual. And as a result, the passengers on the train become richer or poorer as a result of that robbery. And in the case of the membrane, the charge on the capacitance becomes greater or becomes less as a result of that difference. Now, I'll make a big deal of this and talk about it as much as I have for a whole 10 minutes, because it is really a confusing point, and it is worth taking 10 minutes and thinking about it a while in your mind so that when it comes up again in some other context, you can say to yourself, yes, it really is true. We begin with I am. We don't end with it. It is the demand made on the membrane by its neighbors that then the membrane has to fulfill through the ionic current and through the capacitive current for any residual. So with this thought, and within our week of working on the track, I show you this picture of the dormitory sidewalk that's in front of one of the dorms at Duke University. And I put this picture up here because of the sidewalk, the track, if you will, down which hundreds of students flow each day as they go back and forth to their dormitory rooms. If you looked at this set of items in the picture and said, what's most important? Well, of course, it's all important. And the buildings are in a way like the train, and the sidewalk is in a way like the track. And both are essential. The system as a whole won't run without having both of those elements present. Thank you for watching. We'll move on to the next segment.